In this lesson we're going to look at oblique planes. So first of all, an introduction what they are, then looking at their true angles to the horizontal plane and vertical plane, then we'll look at points on them, then we'll introduce laminas, then we'll do a small bit of robatting a lamina to get its true shape, then we'll look at dealing with an oblique cutting objects, and then finally we do a small bit more on true shape and robatments on oblique planes. So first of all, just a small bit of revision looking at auxiliaries. So what we have here is we have a line and we have the elevation and plan of it. Now we want to find the true length of it. So to find the true length of this line, in plan here we look at 90 degrees to it, and then we get our height then from our elevation. So we mark off our height then in our auxiliary. Now this gives us our true length of our line, but the other thing it also gives us is it gives us the angle in which this line is making to the ground. So this here is the true angle in which this line makes with the ground. So if we were to look along the true length, we can actually see the angle on which this line makes to the ground as well, using this method. Now if we look along the length of the line then, so from previous lessons we'll know that when you look along a true length, you'll see the line as a point. So they're the key concepts here. So if you look perpendicular to a line in plan, get the heights from elevation, you'll get the true length of the line, and then if you look along the line you'll see it as a point. Now this here is a similar question. The only difference in this question is we're going to look 90 degrees to the line in elevation. So we set up our x1 y1 line, we establish our widths now from our plan. Now we've got the true length of this line. Now the reason why we might need to be able to do this is the angle here from which we found here is the true angle in which this line makes with the vertical plane. So the back wall where xy is in plan, imagine this is the back wall rising up off the sheet. This here is the true angle in which this line makes with that back wall when we see the true length of it. Now again, if we look along a true length, looking down along the true length, set up x2 y2, measuring back to the previous xy line, we will see the line as a point. So we see a point view. Now in this question here, which is quite common, what we have here is a pyramid, and we're asked in this question to find true angle in which surface A makes with the horizontal plane. So the true angle A makes with the ground. So what we have to do here is look along one of the edges. Now we'll notice that the edge here in elevation is horizontal. That means it's a true length in plan. So any line that is horizontal in elevation, it's going to be a true length in plan because we're looking straight down on top of it. Now this allows us then to look along this line, establish a point. So we're looking along this edge. Then we're going to take another height then, so the height of the pyramid itself, so to get the top height of surface A, mark off that. Now that gives us our true angle in which surface A makes with the ground. So also here, if we have a line 1, 2 on the surface which is horizontal in elevation, it's a true length in plan, and if we look along that true length we'll see it as a point view as well. Now in this question here, what we have is we have a lamina. Now we want to find the true angle that this makes with the horizontal plane. So again, we have to see an edge view. So we'll notice that this edge here is horizontal. So if we look along this edge, set up our x1 y1 line, look along it. Once we look along it, then we're going to get a point view of it. Then we take another corner on the lamina, establish a height for it. Now what we've got is we've got the true inclination which this makes with the horizontal plane. Now looking at planes and traces and where all these traces actually come from. So what we have here is we have our XY line, which is the intersection between the horizontal plane and the vertical plane. Now once we introduce a few other planes into this, they're called traces. So what we have here is we have a horizontal plane. So a horizontal plane will give us a trace, a level trace. Then we have a vertical plane. This will give us a horizontal line and plan, so HT. Now if we introduce a plane in this location here, we'll get two traces. We'll get a trace on the vertical plane and we'll get a trace on the horizontal plane. So we can see the two traces now drawn in our elevation and plan, and we can see where we got them from the 3D view. So if we introduce another one, so simply inclined plane, so it means that it's only inclined at one angle, so it's inclined at an angle to the horizontal plane. So we look at the traces for this. So the trace here, VT, is at an angle, and then the trace and plan now is straight down. Now this here, another simply inclined plane. This time the vertical plane is a vertical line, and then the horizontal trace is a line at an angle. Now looking at a more typical oblique plane where we have both the lines at angles. So what we have in this case here is we have VT at an angle and we have HT at an angle. So then it can also go the opposite direction as well. If in this case the red plane is at a different angle, inclined it in a different direction. So we have V1 T1 and then T1 H1. Now looking at this inclined plane here, what we have here is VTH, and what we're going to look at here is true angles and the angles in which they make with the horizontal and vertical plane. So what we have in this case here, we have an oblique plane, and what we have here, alpha, is showing the angle in which this is making with the XY line. Now this is not a true angle because we're not looking directly in at it. So what we're going to do here is we're going to set up a new angle inside here. Now this new angle, we're going to be 90 degrees to the actual HT. Now if we look at this in more detail, we have our two traces set up, and then what we've introduced here in the 3D graphic is a cone. Now this cone is tangential to the oblique plane, so that means the edge of the cone is going to be touching against that oblique plane. So the oblique plane is resting up against this cone. So what we're doing in the elevation and plan view here is we're going to create this cone. So first of all we take a vertical line anywhere, then where it hits the XY line, so this vertical line is drawn anywhere where it hits the XY line, bring a line 90 degrees to TH. Now this gives us the base of our cone, so we draw the base of our cone here, and then what we're going to do is we're going to draw the side of the cone. Now this side of the cone now is our true angle for which the oblique plane makes with the ground. So what we have here is we have the true angle inside here in the 3D graphic, and then if we were to push this around here, it's the same angle here. So this angle here now is the true angle in which this oblique plane is making with the ground. Now if we want to look at the angle in which this oblique plane makes with the vertical plane, it's something similar. The only difference in this case here is we're going to draw in a cone, this time with the cone, base of the cone facing the vertical wall here. So we take this brown line anywhere again, this time from here 90 degrees to the VT, then we draw our circle or base of our cone, and then what we draw is we draw the sides of our cone now in plan. And what this gives us now is, looking at the 3D graphic, is our cone placed in, and then what we're going to look at is the angle. So the angle, this here is the angle in which the cone is making with the vertical plane. So this is the true angle. So this now can be marked off here. So on the drawing here, this here is our true angle in which this oblique plane makes with the vertical plane. Now this is another method of finding the true angle. Some students prefer this method because it's easier to understand. What we're looking at here is we're going to create an auxiliary. Now the auxiliary we're going to look at is we're going to look along the line HT. Now the reason we're going to look along this line is we're going to now see this whole oblique plane as just a line. And when we look along here, we're actually able to see the true angle then. So we're going to look along HT, create an X1, Y1 line, which is 90 degrees to HT. So what we're going to do is establish up an auxiliary plane here. So we're going to get a point view of HT because it's on the ground. Then we're going to have to get another height then. So we're going to take a height from our elevation. So we need to draw a line in elevation. So you can see in the 3D graphic, if we take a line here anywhere on this from the XY line, what we're going to do here is take this line anywhere on the XY line, bring this point then up to our auxiliary, and then measure this height then. And this here is our oblique plane, and this is the true angle in which the oblique plane is making with the horizontal plane. Now the key thing when we're doing this, and the key mistake that some students make, is this point here. When we're establishing this line here, to find it in the auxiliary, we need to bring it from this point here, bring it up, and then the height is taken from here. Now if we want to look at the true angle in which this oblique plane makes with the vertical plane, this time we're going to look down along VT. So we're looking along VT and seeing this as a point, and then we're going to establish this true angle in which this oblique plane makes with the vertical plane. So again, setting up our XY lines, setting up our auxiliary plane, and then taking a width line this time. So what we're going to do is establish a width line here, and again from the XY line bring it down, and then we're going to take this width here, mark it in our auxiliary, and this here is the true angle in which the oblique plane makes with the vertical plane. Now looking at points and lines on oblique planes. So what we have in this case here is we have the horizontal trace and we have the vertical trace. So what we're going to establish is when we're given views in one view, say a point in plan, how do you find an elevation using our traces? So what we have here is we've took a slice across our oblique plane here. So when we take a horizontal slice across here, we'll notice that this line here is parallel to HT. So when we draw that in plan, you'll notice that this line here and this line here are parallel to one another. Next, if we look at point here, we have a point on our oblique plane. We have the point located in plan. So in this question we need to find this point in elevation. So to find that, for instance, if we take a slice across here, so we're going to take a slice across this. So what that means is if we draw this line then up, bringing it onto the vertical plane, this is how we do it in plan. So this is where this construction comes from. So we've took a slice across here, now we're bringing this slice in, so we're doing the same in plan here because it has to be parallel to TH because it's parallel here in this view, so it's parallel in this view. Then what we're doing here is we're bringing this point straight in our 3D view, so we're bringing it across here. So to do this in this question here, we have to bring it up to establish the height, and once we've established the height on VT as it is here, we're going to bring this point up here, and then bring it across to find this point here. Now again, this is the construction here shown in the 3D graphic. The same construction here, bringing it up here. So this is how you find a point from one view into another view. So if you're given a point in plan and you need to find it in elevation, this is the construction method. Now the line here goes parallel to HT, then it's brought up vertically and then horizontal, and then as in all orthographic, but it is a point in plan, that point is directly straight up in elevation. So what we have here, these two lines here, they're both parallel. So this line is parallel to VT in this view, and it's also, this line is parallel to TH here in this view. Now if we look at this point here, in this question here, we're given the traces and we're given a point in elevation this time. So to do this question here, we're going to bring this point, and what we'll do is take a vertical slice this time. This time it's parallel with the vertical plane. So what we're going to do here is take a line down here, brought back down parallel. Now then what we can do here is, once we have it in this point here, we can bring it straight down here, and then this point brought down here, brought across here, and that's the point found. Now this method could also be done like the previous method, where we have the point here, bring it across to VT, bring it straight down, and then bring it parallel as well. The only reason we're doing it in this method here is because of the slice we've took here, this slicing plane here that we've took here. Now this question here, when we're given one of the traces and we have a point in both views, it is possible then to find the other trace. So in this question here, we're bringing this parallel. Then what we're going to do here is bring it down here, and then point 2 then is brought across. This point now is a point on the trace, and that's how we find our horizontal trace in this case here. So you see it down here in the 3D graphic, the same method again. Now again, this method here, given the horizontal trace this time, and we need to find the vertical trace. So point 2 brought up parallel to HT, then line brought vertically up, point 1 is brought across, and that's a point on our vertical trace. And then you'll see it drawn in 3D graphic here again. Now in this question now we're going to introduce laminas. So what we have in this case here is we have a lamina in elevation, and we need to draw what it looks like in plan. So basically we have 3 points here. The first thing is we'll start off with each points individually. So we start off with point 1, bring point 1 down, and then bring it down parallel to VT. Then once we've brought down to parallel to VT, we drop it straight down onto the horizontal trace and then bring it across. That's point 1 now found in plan. So again, we have it set up here in the 3D graphic again, showing how it's found here using the 3D method. Now we'll do point 2, same method again. Point 2 is found here, so bringing this line down parallel to VT, then where it hits the XY line, drop it straight down, and where it hits the horizontal trace, bring it across. So again, it's reproduced there in the 3D graphic again for you to see. Now we take point 3, use the same method again, construct point 3, and then once we have all the points found, next thing then is we can construct our triangle in plan. Now this question here, we're given the lamina in plan and we need to find the elevation of it. So we bring point 1 up, next we bring point 1 parallel to HT, then we bring a line straight up, and where it hits VT, bring it across, and that's our point number 1 found. Now we'll do the same in the 3D graphic here, just to show where all this construction is developed from. Then we'll move on to point 2, similar method again, and then we go on to point 3, find point 3, and then construct it again. So this here is our elevation. So basically what we're doing is take our 3 points, bring them parallel to HT, bring them up from the XY line onto VT, and then bring them across, and then locate our 3 points. Now in this question here, we're given the lamina in both views. What we need to do here is construct the vertical trace. So how do we find the vertical trace if we're given the surface and given one of the traces? So what we do in this case here, point 1 here, bring it parallel to HT, and then from the XY line bring it straight up, then from point 1 then bring it across, and this here is our point on our vertical trace. Now we can do the same from point 2 here, bring this point up, bring point 2 across. This is another point on our vertical trace, and this here is our vertical trace. Now we only need to do this for one of the points because we have T here, but if we didn't have this trace here, we could have found this vertical trace using this method here of these points here. Now in this question here, it's slightly different. What we have here is we have a lamina, and what we're told in this case is this lamina is part of an oblique plane. What we need to do in this case here is actually find the traces. So to find the traces in this case here, it is a method of extending on the length of this lamina, making this lamina bigger until it actually cuts into our horizontal plane and our vertical plane. So what we can see in the 3D graphic here, we've taken one of the edges, edge 1, 3 here, and extended it until it hit into the ground. So this shows how to establish this point here. So what we're going to do here is we're going to do this in the graphic here. So we're going to extend point 1, 2 until it hits the ground. Now what we're going to do is bring this point down, and then do the same in the plan view here. Extend 1, 2 here. Now this gives us a point on our horizontal trace. Now what we need to do is we need to do the same for one of the other edges here. So we extend on this edge here. So this edge here is extended on, brought down, and then if it's extended on in one view, it has to be extended on in both views. So we extend it on here. This gives us another point, and that's how we establish our horizontal trace. Now once we have our horizontal trace constructed, it's quite easy to find the vertical trace because we'll go parallel to the horizontal trace from one of the points. Or in this method, what we're doing is we're extending on the line 3, 2, bringing this line straight up, and then extending on the line 3, 2 in the elevation view here. So this is the alternative method of doing it. Whereas another method would be if we took point 3 here, or take point 1, so we're taking point 1 here. Now this here is parallel to TH, then we're going to bring this line straight up and then bring point 1 across. It gives us a point on that vertical trace. So there's two methods of to construct this vertical trace. Now if we're looking at this question here, this question involves rabattement and rabatting around the oblique plane until it's laying flat on the ground. And the reason we need to look at this is when we rotate this flat on the ground, what we'll then see is we'll see the true shape of this red triangle in this view here. So what you'll see in the 3D graphic here is we're taking this and going to rotate it now onto the ground. So fold it flat on the ground. So what we're doing in this case here, we're using the horizontal trace as a hinge. So this here is a hinge, say example a door hinge or a piano hinge, and what we're doing is grabbing hold of this oblique plane and folding it down flat on the ground. So this is when we look straight down above, looking in at 90 degrees now to this, we'll see the true shape in plan. So if we look at this method here and how it's done, we have our two traces here and we have the elevation and plan of a lamina. Now what we want to do is find the true shape of this surface. So there's two methods to do this, but we'll look at the first method first of all. what we're going to do is robate around this oblique plane first of all. So what we do is we take a height here from anywhere, using T as our center point, rotate this point around, then in plan from this point here go perpendicular, and then extend out this line until it cuts into our arc here, thus giving us our vertical trace now when it's folded down flat onto the ground. So this now is what it looks like when it's folded flat onto the ground. Now we're going to do the same now with our object. So we want to take our object here and fold this flat on the ground now. So how we do this, first of all, we need to bring all these points in elevation onto our vertical trace. So we're bringing this point 1 onto our vertical trace, then we're rotating around, and because we brought it onto our vertical trace here, we're going to have to bring it back. So when we're bringing it back, we bring it back now parallel to our horizontal trace, and what we're able to do then is point 1 then is brought 90 degrees through the horizontal trace, because imagine if it's hinged up here, it's going to go through this horizontal trace at 90 degrees, and this is point 1 established. Now if we look at another point here, so we take point 2, bring it across horizontally, robate it around, then bring it back, and then 2 brought out. Then the next thing here, we do the same for point 3, robate it around, and point 3 then is found, same method here. So this is point 3 found, and then we can construct our true shape here. So this is our true shape of this triangle using this method here. Now if we look at this again, we take our height here, robate it around, then take this point here, bring it through 90 degrees, and construct our vertical trace again. Then in this case here, what we're going to do is bring point 1 across, bring point 1 then down here parallel to HT, and then construct point 1 then out to this point here. And once we've this done, we do the same for each of the other points now. So point 2 is brought across horizontally, robated around, then brought back horizontally, and then point 2 is found. Then point 3, same construction, bring it across horizontally, robated around, then bring it back horizontally, and then bring it down at 90 degrees. Construct point 3, and then construct our true shape of our triangle. So this here is the method of robating around shape here. So key things here to do is bringing it horizontal here, and then once we've brought it back here, to bring it back horizontal here, and it's horizontal to HT here. Now we're going to look at objects being cut by oblique planes. So what we have here is we have a prism, a square prism, and what it's going to be is it's going to be cut by an oblique plane. So what we're doing in this question here, we're going to establish what the elevation looks like, and then in the 3D graphic we're going to establish this oblique plane and show how this oblique plane cuts through this object here. So it's the top section of this being cut off. So what you'll notice here is our elevation isn't correct. Our elevation should look like this. What we'll notice is the plan won't change because we're looking down from above, so it'll always remain square. So the method of doing this here, we have 4 points here in plan, so it's a matter of finding these 4 points, bringing them parallel to HT, then bring it straight up, then bring point 1 across. Then we do the same with 2, so point 2 is brought parallel to HT, then brought straight up onto our vertical trace, then brought across. This is point 2 established, then point 3, the same method, bring 3 across, and then point 4, same method. Once we have the 4 points established in our elevation, we can join them together, and then we can finish our elevation. So this here is the elevation now completed of this simple object. Now if we look at a cylinder that has now been cut, so it's the same process again as what it is here. If we look at the 3D graphic, what we notice here, it's going to be an elliptical shape in elevation. Now the plan view doesn't change because we're looking down from above. So to do this, we're going to divide our circle into 30/60 to give us 12 points, to give us our best possible elliptical shape. So we take each of these points, bring them up to our elevation first of all, and next what we're going to do is bring all these parallel to HT. So what we're going to do now is bring all these points parallel to HT. So in this case here, we're bringing point 1 across here, bringing it up and bringing it parallel to VT. So this here is a second method of how to do this question, where we're bringing point 1 here, bringing it horizontally across here, bringing it up here and bringing it up at an angle here. Now the reason we're doing it in this method this time is because what we're doing here is we're saving the amount of construction lines we have to do. Because if we were to bring point 1 or point 2 up here, point 3 up here, point 4, we'd have different lines for each of this. Whereas in this case here, if we bring a horizontal line here, bring a vertical line in this case, and then bring it parallel to VT, it'll allow us to get 2 points at the same time. So it's a slightly quicker method. But if we want to stick with the previous method, we can do this also. It would still work, it's just a small bit more time consuming. So this here is our elliptical shape here is found. So we have our ellipse points found. We can draw it in heavy and we can construct the sides of it. Now in this question here, we're looking at a pyramid that has been cut by an oblique plane. So first of all, if we look at what's happening in the 3D graphic, this here is what's being chopped off the top of the pyramid. So we have to look at a method of constructing this and how this is done. So looking at this here, what we'll notice here is there is no points in plan here that we can bring up and bring onto VT and find out where they're cut. So in this case here, we have to set up an auxiliary. Now the reason we set up an auxiliary is when we look in at the auxiliary of an oblique plane, we can see actually what it's doing to the object, so where it's cutting through the object. So in the 3D graphic here, you can see in the auxiliary view here, you can see the trace here cutting through this object here, so you can see what's being cut. So it's a matter of bringing these points back then to plan. So to do this, we look along HT in plan, set up X1, Y1, and then we can construct our pyramid up here, bringing up all our points. So what we've done here is we've constructed our pyramid. Now we need to construct our traces. So we've already the horizontal trace because that's going to be a point view. Then we need to take a vertical measurement for our vertical trace. So we take this measurement here, bring it from the XY line up, then take this height and mark it off. Now again, it's really important you bring this measurement up from the XY line and not from this point here. This is a really common mistake that students make, bringing this point up from here. It has to be brought from the XY line up the way and then take this height. So this here is our vertical trace now put in. Now this gives us points here, 4 points here, on which is cutting the pyramid. So these 4 points are brought down to plan and marked off. So these are our 4 points being cut. Now what we can do with these 4 points is bring them up to elevation. And we can bring them straight up because they're on lines already. So we can draw it in plan, draw it in elevation, and then complete the drawing. So this is what the object looks like when it's been cut by an oblique plane. Now in this question here, similar question here, only it's a hexagonal pyramid this time. So again, to look at what's being cut, so we can see the object being cut here in the 3D graphic. What we're going to do is have to use the auxiliary method again here. So again, we're going to take our auxiliary looking in at 90 degrees to HT, construct X1, Y1. Then what we're going to do is construct our pyramid first in auxiliary. So we've our pyramid constructed. Then we're going to establish a height for our vertical trace. Then take this point from the XY line, bring it up to here, then mark off the height. Then construct our vertical trace. Now, what this allows us to do then is establish what is being cut. Now, what we have here is all well indexed here, so we know that this point here is brought back onto the line 1. So what we're going to do is establish each of these points now and bring them back down to plan. So we have this point here brought down, next one then brought down, and so on, and follow around in a pattern like this. So this here is our points in plan. Then we can bring them straight up, establish them in elevation, and then we can construct it in plan, and then do the same in the elevation. And that's what our hexagonal pyramid looks like when it's been cut by an oblique plane. Now, in this case here, a small bit extra construction because we're dealing with a cone. So anytime a cone is cut by an oblique plane, what we can look at here is it's going to be an elliptical shape. So what we have to do here is, similar to all the previous ones, look along HT, then establish our cone in auxiliary, and once we've our cone established, we construct our vertical trace. So we have our vertical trace set up here. Now, so what we have here, and what we notice here in this question here, is we don't actually have any points here in plan, so we're going to have to establish what points are being cut. So the easiest way of doing this is establish generators from the base of the cone. So we're going to establish these generators from the base of the cone. So you'll see in the 3D graphic here, if we establish these generators here, it'll allow us to get points on this elliptical shape. So to do this, in plan, we divide our circle 30-60, and what we're going to do in this case here then is mark it, index it 1 to 12, bring up these generators up to the auxiliary, construct them to the apex of the cone. This will give us all our points that we need to construct. So we've now got all our points down along the cut surface now. What this allows us now to do is we can bring all these points down now to plan. We've also generators constructed in elevation, so all these points can be brought down to plan now, and we can establish our cut here using all these points here. So these are all our points constructed here. Now it's a matter of just bringing them up. So we've brought all these points up. Now you'll notice that one of these points here was brought straight up here, and obviously you won't be able to find it, so what we're doing is we're going to use our traces. So we constructed a line parallel to HT, brought it straight up across, and that's how we found this point here. So that has to be done in two locations here for point 1 and point 7, but all the rest of the points can be brought straight up. So this here is the elliptical shape constructed in plan and then constructed in elevation, and we finish off the outsides of the cone then. Now what we're looking at is getting the true shape of a cut surface. So what we have here is we have an object that has been cut by an oblique plane, but what we have to do in this case here is we need to construct the traces first of all. So to construct the traces first of all, we're going to extend on the edge 3, 4, do the same in plan, extend it on, and we've brought it down then from our elevation. That gives us a point here. Now we're going to do the same for one of the other edges. So we're taking edge 2, 3, bringing this down, then take the edge 2, 3 in plan. This gives us a point. Now we've constructed 2 points on our horizontal trace. Now want to find a point on our vertical. So what we're doing here is, in this case here, we're extending on 2, 1, bringing this line straight up, and then extending 2, 1 here in the elevation. This gives us a point on our vertical trace. Now, so what we've now constructed is we've constructed our traces. So what we want to look at is find the true shape of this surface now. So to get the true shape of this, basically we're going to take a line here anywhere, rotate this around, and then from this point here go 90 degrees. This gives us our vertical trace when it's folded flat on the ground. Now what we have to look at is how we get this again. So basically we start off with point 2 here to bring it horizontal, rotate it around. So this here is being rotated around to this point here. Now once we've brought it to this point here, we need to bring it back horizontally across again, and then point 2 here brought out at 90 degrees. This gives us point 2 here. Now this has to be done for each of the other points. So we look at point 1, brought horizontally across, then marked off. Then once it reaches V1T, brought in, and then 1 is point marked off. Now we do the same for 3 and do the same for 4. So what we have now is we've our true shape of our surface found. Now in this question here we're going to look at a pyramid that has been cut, and we're going to look at how to get the traces and then look at the true shape of this surface ABCD. So what we're going to do first of all is establish where the traces are. So we're extending on the edge CD. So this edge is brought down to plan then, and it's extended in plan also. So this gives us a point on our horizontal trace. Now we have to do the same with another edge. So we take the edge BD this time, extend it now in plan, and this gives us our 2 points on our horizontal trace. Then what we'll do is we'll establish another point on our vertical trace now. So what we've done here is extended on the edge BD until it hit the XY line, bring that straight up, and then extend on the edge AB in elevation. That gives us our vertical trace. So now what we've done is we've constructed our traces. Now what we're going to look at is doing our rotating of the object. So we're taking a measurement here. We're taking this measurement, measuring it out here, 90 degrees. Then in this case here we're just rotating around the opposite direction here, and then we're establishing V1T. Then what we're going to do is take our points here. So we have 4 points here, bring them across horizontally, mark them onto VT, scribe them onto VT1, and then bring them back horizontally, bring A out, and same again for point B, point C, and point D. And there are points established. Now we can draw in the true shape of this object then. Now if we look at this, this is another method of finding the true shape, and sometimes we'll use this method if we have the auxiliary already set up. Now what we have here is we've the auxiliary set up here. So the reason we've set up the auxiliary here is we needed to find the points A, B, C here, to find them in plan. So we're bringing them back down here. So we've each of the points here found. So we've the cut surface found. We'll bring it up to elevation and basically draw it in plan heavy, draw it in elevation heavy. Now in this question then we want to get the true shape of this surface here. So to get the true shape of this surface here, we have it up here. Basically we're looking at an edge view of it here. So what we're going to do here is fold this down onto the ground, and then what we'll do is find it down in this location here. So this is another take on the rebatment method. So what we're going to use here, we're going to use HT as a hinge, and what we're going to do is take this edge and fold it down flat onto the ground. That means we can bring these points down onto the ground. So we take point A, rotate it onto the ground. We have it on the ground here. And what we're going to do is bring it straight down here, and from A here, bring it out 90 degrees. Because it's folding out along HT as well, like a hinge. So that's point A found, and then point B is found, same method, point C, and then point D. So this method is used when we have the auxiliary already drawn, and it's an easy method of just rotating this flat onto the ground, and that's how we get our true shape in this question. So this here is looking at the two methods, so comparing them side by side. So one is where you don't have an auxiliary, but you have the cut surface here given to you, and you have to find the traces. In this one here, we were given the traces, but we had to find the cut surface. So the two methods are shown here. So we take point A in both cases. Point A is brought across here, rotated around, then brought across here horizontally again, and brought out 90 degrees. So that's point A found in this one. In this case here, A is here, folded onto the ground, brought down here, and then brought out 90 degrees. So there are the two methods in this method of finding the true shape of that cut surface.